So hello and welcome everyone to this new video in our OpenGl ES series. In this video, we will be looking back to our sphere, namely the sphere which we created using the icosahedral. If you remember, we had a problem texturing this sphere. In this video, I will show how we can solve this problem using Cubemaps, which we introduced in the previous video. Then we will create a solar system. So I put the name here between quotations because we will not be creating a realistic solar system. We will only have the sun. We have a sphere representing the sun and another sphere rotating around it. And the path of the Earth around the sun will also not be realistic compared to the size of the Earth and the sun. Then I will add another button to our activity, and this button will be used to switch the camera view. So let's start coding. So this is our program from the previous tutorial. We have the Earth rotating inside a skybox, which I tried to make it looks like the outer space. If you remember, we have this sphere vert2 here, which was created using the spherical coordinate system. Let's create this using the icosahedral. Class for that is sphere vert. Let's change this, and it take only the number of divisions. There was no scale here. We can add that if we want. And for the divisions, let us put 2, for example, and let's rerun. You can see the problem here in this side. Let me remove the wireframe object and make the subdivisions less so that the problem will appear bigger. And let's rerun. Let's go back to 1. So now you can see here we have the problem. I think if we are not rotating, we can see the problem even more evident. So this is the part I'm talking about. Let's try to correct this using the Cubemaps which we created in the previous tutorial. So if you remember, we have this skybox which use Cubemaps. Let me copy this class and let me call this sphere object. So inside this sphere object, we want to use this sphere vert. Create an instance from that, and then we use this sphere vert to get the positions. We need to pass here the division. And if we want to scale the sphere, it's enough to scale this float array here. So we already have a function for that in our mat utils, and it's called scale. So we pass the array we want to scale and the scale. Everything here should stay the same as before. So we want to initialize the stride and the number of vertices and then our texture array. So these are only the paths of the images. And now in the onInit, we will be using a program which is similar to the one used in the skybox. So let me copy those. Let me call it cube texture normal. And let me use this name here. So the rest of the init still the same, since we need to initialize the vertex buffer and load the vertices to it, use the program and initialize the positions, and then load the cube texture. Also update and destroy is not changed. So in draw, if you remember, we had this depth functions which we were changing. So to make sure that the skybox is rendered, let me remove this because it's not needed. And let's go to the vertex shader. So in the vertex shader, we were using this trick here. We were putting the Z equal to the W parameter of the position. We don't need to do that here. So we can directly put the GL position to position. And then we use that in computing the texture coordinates. And now, since we will be looking at the sphere from the outside, not from the inside, we need to go back to a right-hand coordinate system. But let me leave this for now so you can see the effect which this will have on the sphere. Now let me save this, and that's all. Now we can use this sphere object. So here, instead of using the BCT object, we will use directly the sphere object. And it takes a scale. Let's put the scale to 1. The divisions, let's put them to 2. And then we need to put the textures. So this is very similar to what we put here in the skybox. Let me copy those. And I already prepared the cube map for this tutorial, and I put it inside images. Earth here, you can see we have these 6 images similar to what I did here in the Milky Way. So I only need to change the name of the folder here. And that's it. Now we can run. Yeah, this wire object was using these vertices, which we have now inside the sphere object. We will not be displaying the wireframe here anyway, so let me comment it. So as you can see, now the problem is removed. And let me rotate the sphere. So no problem in rendering. However, if you look closely, you can see that there are some kind of flipping here. Let me show you the map of the Earth. So you can compare here that everything is flipped because we are using a different coordinate system. So if we are looking from the inside, and that can be done simply by changing this scale. So let me make this scale a little bit larger so our camera will be inside, or we can actually just move to inside the sphere. Now the texture looks better, but maybe it's better to make it bigger actually. Let me put this scale to 30. Camera is at 10 meters, so it's already now inside the sphere. And now you can see that here the South America, now Africa, everything looks correct. So let me put the scale back to 1 and switch the coordinate system here, put it to normal. And now we can actually directly assign GL position here, and we don't need this line. And let me now run. So you can see the texture look correct, and that's it. And now we have a sphere model which is built using the icosahedral, which is rendered correctly. So let's start building our simplified solar system. And for that, we need to add the sun and the rotation model of the Earth around the sun. So as you can see, for the sun, I already prepared a texture here, sun.jpg. And for the rotation model, I also prepared a class. Let me copy this and put it inside the custom objects. This class, I called it pathvert. I'm not putting too much attention to the name. Maybe this is not the best one here, but let's see what this class does. This class implements the elliptical orbit of the Earth around the Sun. So I took the main equation here from Wikipedia. So this is the page which I took the equation from. So it's the orbit equation. And this is the equation that I will be using. Let me make this smaller so you can see that. So here in this equation, a polar coordinate system is used. That means given an angle theta, we will be able to compute the radius r. So as you can see here, r is the separation distance between the two bodies. So we'll be taking the sun to be in the origin of the coordinate system, and then this r will be the distance from the Earth to the origin. This factor here, L squared divided by m squared by mu, I simplified this expression here and I called it scale. And then the only parameter left which we need is this parameter E, which is the eccentricity, as you can see here. So now giving a scale, an eccentricity, and a theta, we can compute the radius. And that's what this function does here. So we only need to divide the scale by 1 minus E multiplied by the cosine of theta. And then we can convert our polar system. So we have r and theta. We can convert them to x and y simply by multiplying this r by the cosine and sine respectively. Then I return the r, x, and z coordinates. So note that we are talking a planar coordinate here. So we are assuming that this ellipse is contained in the xz plane. And then later we will add the y coordinate for that, which is fixed. And that's done in this function here, the function we will call to create the path. And in this function, we give the parameters of the elliptical orbit, the scale, and the E, and number of points, which give us how fine our path is, and then also the y coordinate. And the rest of the function is simple, so we create the buffer to hold the 3 coordinates x, y, and z, and this path will contain the number of points plus 1 because we will start and end with the same point, and then we loop over these points, and every time we compute the angle theta, which is simply the current index I divided by the number of points multiplied by 2p. And we call our function ellipse to get the x and z coordinates. This was here for debug purposes. We can comment that. And then we put our X, Y, and Z coordinates. And when the loop is ended, we return the buffer. So that's all what we need for now. We can go now to our activity and we can add a sphere representing the sun. And since I don't have now a cube map for the sun, I will be using the previous way of rendering a sphere, and that is using the spherical coordinates. So I will be using this sphere vert2 object which we created previously and get the vertices with the texture from it and use them in this PCT object. I think we don't need this parameter here. And for rotating the sun, I will do that in this function called move sun. I will create it inside our activity. And for moving the earth, I will also use a function move earth. So this is our earth. Let me refactor this. And here I will be calling move earth, and let me create this inside our main activity. So actually move the sun is very simple. As before, we will just rotate this object around the y-axis with a certain degrees. However, for the earth, we will be using a variable called theta, and inside this move earth function, let me put the theta here above the move earth, and inside this function move earth, we will be changing this theta every time with a certain step. So as you can see, this step is 1 degree. However, the value of theta will be now in radians because this function ellipse expect radians. And let me add the import. Then so this function ellipse will take the scale, which as you can see here, we are putting it to 3, and the eccentricity, which I'm taking to be 0.5, and the angle theta, and it will return for us the R, X, and Z. So we'll be using the X and Z parameter and putting the Y parameter to 0, and then we'll reset the translation of the Earth. So we'll put it back to the origin. Then we rotate it by 5 degrees, and then we put it in the new position on its elliptical orbit around the sun. And that's it. Let's now run the program. You can see the Earth is rotating, but I cannot see the sun. Let's see what the problem is. Yeah, so we have not added the sun to the scene, so we need to add mscene.add object sun, and let me rerun. And now you can see we have the sun rotating around itself. The Earth is rotating around itself and going in an orbit around the sun. In the path vert, we already created this function, which will help us also to draw the elliptical orbit of the Earth. Let me do that. So remember, we have this wire object, and let me create a new instance of it. And I want to initialize this wire object using an elliptical orbit. And for that, let me first prepare this float array representing the vertices. And to create that, I will be using the path vert and the function generate ellipse. Remember, for creating this orbit here, we were using a scale of 3 and an e parameter of half. So we use the same here. And let me put 100 points. Since we did not translate the Earth or the sun on the y-axis, we will put y to 0. And now we have our vertices. I only need to add float here. And then we can assign those vertices to the wire object using the function set vertices from path. And yeah, I should not forget now to add this object to the scene. And let us rerun. So you can see now that the Earth is following this path. Maybe if we moved a little bit on the z-axis, on the y-axis, you can see it now more clearly. And you can see that this orbit is elliptical. Let me, however, change the color of this orbit. For that, we can use the function setColor, where we need to assign 3 values to the red, green, and the blue components. These values should be between 0 and 1. Let us rerun now. So we have a brownish color here, which looks better. Yeah, and that's it. Now we have the Earth rotating around the sun. Of course, we did not tilt the axis of the Earth, and you can see that in one turn around the sun, the Earth is not rotating 365 times around itself. I will say. For this scene, I wanted to add a bird eye view. So I wanted to put the camera at the top of the scene and looking down. So I decided to do that by adding a button here. And by clicking on this button, I will be switching between bird eye view and this current normal view. So let's do that. So let us first add the button. For that, we go to the layout folder and we select the activity main. And let me add the button here at the bottom of this file. As you can see, I called it change view image button, and I put the width and height and the constraints, so it will appear here at the top left area of the activity. And for icons, I used an icon provided by Android, and it's called presence video online. So let us go now to the main activity, and in the onCreate function, we can set a click listener to this button. I called this function here change view, which will be called by when this button is clicked. And let me paste the code of this function. So for this function, as you can see, I have a variable called current view, which is initialized to 0. And then whenever the button, whenever this function is called, we look at this variable. If it's 0, we change the default parameters of the camera view correspondingly. So if it's 0, we will set the camera position to be 10 on the z-axis, and we will be looking in the minus z direction. And if it is 1, then we will put the camera at 25 at the y position, so it's above the scene. It has a small offset here on the z, and it's looking mostly down, as you can see here on the y-axis. So let us create this function, set default view. And if you remember, we have this default position and default orientation in our camera class. In this set default view, we can assign values to them. So we simply need to put our default position equal to the parameter, the first parameter of this function, and the default orientation equal to the second parameter. And then we reset the camera. That's it. As you can see, we change the camera default view here, and then we change the value of the current view. So if it was 0, it will be 1, and if it is 1, it will become 0 after taking it with mode 2. So let's run now. So this is the button which we have just added. And by clicking on this button, the first time the view is not changed, and that's because I started here by value 0. So I can start here by value 1, and let me rerun. So it will start with this view, and then by clicking on this button, we will get the bird eye view, and then we will go back to the previous view, and so on. That's all what I wanted to show in this video. If you like it, please give it a thumb up and subscribe the channel, and I hope to see you in the next video. Bye.